Well, hey, AP Bio students, Mrs. Shelton here, and just posting a Screencastify for you for Chapter 2 from our textbook, Chemical Context of Life. So I do want to make sure you're really clear. We'll talk about this on our Zoom lecture, but this section that I'm putting up here, the You Must Knows. So this is actually coming from the Test Prep Review series. So starting in chapter 2, this is where they're actually highlighting for you what is it from this chapter that you should be able to explain the College Board is expecting you to be able to understand. So here it's what are the three subatomic particles, the types of chemical bonds, hydrogen bonding, properties of water, pH scale, and then also this new concept after pH, understanding what buffers are for. So I'm going to try to include these for you, but they're also for each section in this test prep review series, but that's where that is coming. Now, also, again, you do have your notes, and then you also have your free response questions practice that is specific to Chapter 2 content. So do be sure to answer those questions. Now, do remember also that your notes and free response questions are due before you take a test. On a test day, we will have plenty of time to go over the content and to help you understand the material so you feel good about what we are talking about. So let's get this in the view we want it. So what you guys are seeing here is you're seeing these, this is chemical warfare. This is freaking awesome. So get this here. So biology is just cool. It really is cool. And we start seeing like chemical warfare and understand the chemical makeup of living things, and we understand the biochemistry of living things. I will personally tell you that I was not a fan of chemistry when I took it in high school. I was not a fan of chemistry when I took it my first year of college. But once I started taking organic chemistry and then I took my biochem class and I started taking advanced level biology where it's like, oh, it all fit together. That's where I really gained a true appreciation of chemistry. Because when we want to ask the question of why does this happen and what does this do? Well, we always have to get down to that chemical level in order to truly understand biological processes. So this chapter is really going to be a review of your sophomore year chemistry class that you took, making sure that you're caught up on that before we start adding new content to it. Now, in this diagram, what we're actually seeing is you're seeing sodium, what it looks like by itself. You're seeing chlorine, what it looks like by itself. You know that sodium is an element. So this is all sodium, this is all chlorine. But we also know is that these have unique properties to them. They look different than each other. But then when we combine them into a compound in sodium chloride, it now takes on that emergent property of being this white crystalline structure that is your table salt, a sodium chloride. But understand elements. We can find all elements on the periodic table, but then we also have to understand bonding and why different atoms bond and how they bond in order to then understand the compounds that are formed. When we do talk about living things, we should be able to identify the fact that oxygen, carbon, hydrogen, and nitrogen make up the majority of the mass of living things. And then we have phosphorus and sulfur that also make up they make up our proteins and our nucleic acids. And then we have all of these trace elements. And so these trace elements down here, and so we do need like cobalt, you need tin, you do need iodine. These are trace elements that we absolutely need, less than 0.01% of mass, but without them. So if you didn't have iodine in your system as a trace element, well, you would end up having thyroid malfunction and thyroid issues, and you'd have this big old goiter that was protruding from your neck because of this lack of this trace element. So we have all these essential elements. So really you need to know the elements that are part of everything up to protein. But then you should also recognize some of these others and then just know what a trace element is, just the definition of a trace element. When we do talk about an atom, it's assumed that you understand the three subatomic particles. With the subatomic particles, the nucleus of an atom is made up of the neutrons and the protons. Now, protons have a positive charge, neutrons have no charge, but a neutron and a proton do have equal mass of 1 atomic mass unit. Electrons have negligible mass, but they do have a negative charge that's equal and opposite then to the proton. It is number of protons that determines the identity of the atom. And then it's the combination of the protons plus the neutrons that gives an atom its atomic mass. Electrons, if electron number equals proton number, then it is a neutral atom. But if it gains an electron or loses an electron, then it becomes an ion. So again, here is just your review: protons, neutrons, these form the nucleus. This is where the mass is determined. And then electrons then are what actually are involved in bonding. If we change the nucleus, so if this actually lost a proton or lost a neutron, well, now we're talking about radioactive activity that is way different than the covalent bonds or ionic bonds that we're going to be addressing. Now, if we talk about a radioactive isotope. So this is something that you should be aware of, is we should be aware that sometimes in the atom. So with this, this would actually be, this is helium. Well, helium should have atomic mass of 4 because we combine these particles. It is non-reactive because it has a full outer level. Its outer level can hold a maximum of 2 electrons, but when I look at the periodic table and I look at the average atomic mass of helium, the average atomic mass of helium is not 4. The average atomic mass of helium is 4.02, because that means that there's some isotopes of helium that exist. And an isotope of helium would be something that has still the same number of protons, because 2 protons means it's helium, but there might be some atoms that actually have 3 of these neutrons in order to give an atomic mass of 5. And so what you see on a periodic table, though, is average atomic mass. But here we can look and say the atomic mass of this would be 4 when we total up protons and neutrons. So an isotope is that unusual number of neutrons that then for a particular atom. And some of those are radioactive because now with an added neutron or less of a neutron, now the nucleus is unstable. And that's what it means to be radioactive. And there are some really important radioactive isotopes that we will be addressing later on. We do need to remember that the electrons are what are involved in bonding. Electrons have energy levels, and electrons can actually absorb energy and move to higher energy levels where they've got high potential energy. And then they can actually then release their energy and drop back down to their lowest energy too. So do remember electron energy levels. What's most important though for you is not just that you can identify an element, know its atomic number is telling you proton number, the symbol, atomic mass, this is average atomic mass, including all isotopes, but we need to remember the number of electrons in the outermost level. Atoms will react with other atoms in order to satisfy and fill a full outermost level. Now, the first energy level holds 2 electrons, but the maximum number of electrons then that the next energy levels can hold is 8. And atoms will react in order to satisfy a full outermost level. So in ions, what will end up happening is some will lose electrons or gain electrons in order to achieve a full outermost level, or they're going to share electrons in order to then form covalent bonds. So you should be able to recognize that all of your group 1 elements have 1 electron in the outermost level. All of your group 2 elements have 2 electrons in the outermost level. And then we have all the transition elements, but then what we do is we move on to boron. This is group 13. This has 3 electrons in the outermost level. Carbon has 4 electrons in the outermost level. Nitrogen has 3 electrons in the outermost level. Oxygen 2. And so this is also where in this valence shell, this outermost shell, this valence shell, this is also how we predict then the number of bonds. Now in your textbook, a new term that they're going to ask you is, what is the valence of carbon? And if they ask you that, when they ask you what's the valence of carbon, what they're asking you is how many unpaired electrons are there, or how many bonds can carbon form? So you would say that the valence of carbon is 4, or there's 4 unpaired electrons in the valence shell. Nitrogen, the valence is 3. It can form 3 covalent bonds. There's 3 unpaired electrons in the valence shell. Oxygen then can make 2 covalent bonds. There's 2 unpaired electrons. So do be aware when we're referencing the valence shell, that's the outermost energy level. These are the reactive electrons. And then in the textbook, that's new terminology for you when they ask what's the valence, they're asking you really how many bonds can that atom make. So here's just more electron diagrams. So you're seeing Bohr models here just so you can get an idea of what the valence looks like. And then why neon or argon is inert. These are noble gases. Well, they already have 8 electrons in their valence shell and their outermost electrons, so they don't need to react. They don't need to lose or gain electrons, is what needs to happen. When we start talking about molecules, molecules are covalently bonded atoms. They're sharing electrons and they're forming this covalent bond, and they are sharing electrons that are in the valence. So here is just a hydrogen molecule. These hydrogens that had 1 electron each now are sharing. Well, now they both, in sharing this, have a full outermost level. Remember that first energy level can hold a maximum of 2 electrons. Every other energy level then can hold a maximum of 8. So that's the octet rule that we have to be remembering. So oxygen gas is O2. Well, oxygen gas is O2. Well, it forms a double bond. And so what that means is there are 2 pairs of electrons that are being shared, or 4 electrons being shared, is what ends up happening in forming this molecule. Water, we learned as a covalent bond, but it's a polar covalent bond because in this polar covalent bond, there's an uneven sharing of electrons because oxygen is more electronegative than the hydrogen. Also with oxygen, oxygen has these 2 pairs of electrons already that have a slightly negative charge. And then hydrogen, with its just 1 little lone positive proton, gives it a positive charged end. So it becomes a polar covalent molecule. Methane is a nonpolar covalent molecule. So these are evenly distributed electrons about the central carbon is what happens here. So it's nonpolar. Here's my water showing me my polar molecule. So we talked about this with properties of water, but this is a model that we would end up seeing. And we need to recognize the hydrogens have the slightly positive charge to it, and then the oxygen ends have the slightly negative charge to it. This diagram would be an example of an ionic bond. And as an ionic bond, what's happening here is not a sharing of electrons, but here, go ahead and take mine. You can take my electron. I don't want it. I only have 1 electron in this outermost level, and it is bogging me down. And chlorine says, cool, I'll take it because I needed 1. And so it's an absolute exchange of electrons. But then that leaves this to be a sodium ion. So this is a cation. Cations are positively charged because it lost an electron. So now its number of protons in the nucleus, there's 1 extra proton compared to number of electrons. So it's a 1 positive charge as a cation. Now a chloride ion, because now it has 1 extra electron compared to the protons in the nucleus, this has a negative charge. Well, what needs to happen is they need to arrange themselves in a 1-to-1 ratio in order to overall end up having a neutral charge. But this is different from a covalent bond where they're sharing electrons. So this is my sharing of electrons versus then an ionic bond where they're exchange the electrons and now it's their charges that are keeping them together is what's happening here. Salts are formed by ionic bonds. So when you hear that term, salt compounds, they're ionic bonds. If we're talking about molecules, we're talking about covalently bonded atoms in order to form those molecules. Here's the crystalline structure then of salt, and it's just arranging itself in this 1-to-1 ratio in order to satisfy those charges is what's occurring. Now, a third type of bond you absolutely need to know is you need to know what a hydrogen bond is. So we talked about covalent bonds. And so this ammonia molecule is formed by a covalent bond, this water molecule is formed by covalent bonds, but then hydrogen, just being a proton, is still attracted to other more electronegative atoms of other molecules. That's what a hydrogen bond is. So this hydrogen having its positive charge, this nitrogen on a different molecule having a slightly negative charge, because this is a polar molecule too, hydrogen is attracted to the nitrogen, that forms that hydrogen bond is what we're seeing there. You're going to see different models of how molecules are written. So just be used to the fact that this is the same as this. This methane is the same as this methane. It's just different models in order to help you understand the shape and the structure of that molecule. Now, it's also when we talk about molecules, and especially large organic molecules, where form fits function. We have lots of molecules that are signal molecules and are for messaging. Well, it's the shape that matters. Shape actually has to match then the shape of the protein that it's sending a signal to. So in molecules, especially when it comes to proteins, form fits function. The shape of the molecule matters, so it now has a job to do. We talked about properties of water. We did a worksheet on properties of water. So here, the biggest thing we need to know is that a single water molecule will make 4 hydrogen bonds with other water molecules. So what you're seeing here is you are seeing this property of cohesion, where water is attracted to other water molecules. And it's this cohesion that actually does give water a lot of its unique properties. So this is why there's a high surface tension of water. This is also why water has a high specific heat in order to break those hydrogen bonds. This is why water has a high heat of vaporization. And it's also these hydrogen bond interactions with other water that actually leads to water being less dense when it's frozen, when it becomes solid. So those would be some properties that you should be aware of. Now, water also has the property of adhesion. Water is attracted to other polar substances. So water being able to stick to these inner walls of the xylem of a plant, that's a property of adhesion. But then water wanting to hydrogen bond with other water, that's a property of cohesion. And this is what is helping water to move up the xylem, that vessel system, up a tree and out through the leaves. Here we've got a spider on the water. Well, the spider is not sinking because of the surface tension that water is exhibiting at the surface of this particular water system. We also know that water actually allows for very mild temperatures in an area. But when you actually live by a large body of water, water has the ability to absorb a tremendous amount of heat energy before changing temperature. So with that, you look at the coastal regions of California where we've got this cold climate that comes down from Alaska. And with this particular cold climate that comes down from Alaska, well, along the coast, average temperatures are in the 70s, but then you move away from the water, and now that heat is not being absorbed by the water and serving as this heat sink that can absorb a lot without changing its temperature itself. And it's that high specific heat that we're actually seeing here. Here's a graph for you guys that you made when you were in chemistry. This was the most exciting lab you did in chemistry. And so what you did is you graphed water or ice melting and then boiling is what ends up happening. So what you guys saw is there, for water in ice form and solid form to actually turn to liquid form, it actually has to absorb a tremendous amount of heat energy is what ends up happening. So you had your ice on a beaker, you had your thermometer in there, and for ice to turn to liquid, well, it absorbs a tremendous amount of energy. And then as liquid, well, those molecules speed up, speed up, speed up, speed up. They're breaking and reforming those hydrogen bonds. And then before it turns to a gas, this high heat of vaporization, there is a tremendous amount of heat energy that needs to be absorbed by that water in order to get that water to now break away and go into gas form. So this high heat of vaporization is actually why we sweat. This is why a kangaroo is actually just going to lick itself in order to then let the saliva evaporate off. But it's that evaporation, that change from water as a liquid to a gas, that is removing a tremendous amount of heat from the body. With water being most dense at 4 degrees Celsius. As water stops moving, it gets more dense, more dense, more dense. At 4 degrees Celsius, it's the most dense. But then at 3 degrees Celsius, 2 degrees Celsius, 1 degree Celsius, as these water molecules stop moving to become solid, they have to arrange themselves in order to satisfy hydrogen bond interactions. And so they actually, with water, actually in this crystal structure, this is actually going to make the density less. So this is why ice, so when water becomes solid at 0 degrees, its density is less than liquid, and we see ice up on top. And this is why we end up still having aquatic life that lives underneath in a frozen lake. That frozen water with its lower density acts as an insulator to keep any heat from the water in and also prevent that heat loss too. Water is a universal solvent. You should be able to look at a diagram like this. So here's my sodium chloride and my ions that are being dissolved in water. Well, if we look at this, if I didn't have these charges, you should be able to look and identify, if you just saw a green ball here and I told you that it was an ion, you should be able to tell me that, oh, yeah, it's a negatively charged ion. And I know it's a negatively charged ion because of the arrangement of the waters around that ion. All of the positive ends are attracted to the negative ends. We remember that opposites attract. Here I can tell that this would be my positive cation because all the negative ends of oxygen are attracted to the sodium. Water being a universal solvent, well, here is this big purple blob. Well, this is a protein. Well, water can dissolve great big proteins because of all of these hydrogen bond interactions. With those proteins, we learned what amino acids are, and amino acids still have highly electronegative atoms attached to them. There's the nitrogen and the oxygen that's still there. So with that, we have water. These polarities are attracted to each other, and water can create this hydration shell. It can surround these large macromolecules because of its polarity. When we do talk about chemistry, it's important that you understand these basic definitions and representation of a chemical reaction. It's important that we know in a chemical reaction, we have reactants. This is what we start with. And then we have the products. Now, law of conservation of mass applies here as far as, and conservation of matter applies here. What we start with, we also have to end with. That's why we have balanced equations. But also when we look at a chemical equation, something else you guys are going to see is chemical equations that are in equilibrium. So if this was an equilibrium where I had a forward arrow and I also had a backwards arrow, what you should recognize with equilibrium, something like this, is that the forward reaction is occurring at the same rate as the backwards reaction. It doesn't mean that the reaction has stopped. It means that the rate of the forward reaction is the same as the rate of the reverse reaction. You should be able to look at this diagram here and go, oh, this is the dissociation of water, is what you should be able to see. And this dissociation of water is in equilibrium. So here's my hydronium ion, here's my hydroxide ion, where one of these waters has lost its hydrogen, the other water then gained it. Well, this is how we determine whether a solution is neutral, acidic, or basic. If I have a basic solution, I'm going to have more free hydroxide ions in solution, less hydrogen ions or hydronium ions. You can look at it that way. If I have a neutral solution, I have an equal amount of hydrogen ions and hydroxide ions. And if I have an acidic solution, I have way more protons or hydrogen ions than I have hydroxide ions. Remember my pH scale? The pH scale is measuring the concentration of hydrogen ions is what it's measuring. So as I become more acidic from neutral, neutral is a pH of 7, where my hydrogen ions and my hydroxide ions are equal. But as my hydrogen ion concentration increases, my hydroxide decreases, well, this is where my pH is going to get lower and lower and lower. And remember that with every pH number that I drop, that's an increase in protons of 10 times greater. We'll talk about that later. So do remember my basic scale. If I'm basic, that means I've got more hydroxide ions than I have hydrogen ions, is what I end up having. Now, an application of acids and bases would be something like understanding ocean acidification. So in ocean acidification, this is the first thing you need to know is atmospheric carbon dioxide. Excess atmospheric carbon dioxide will dissolve in water, creating carbonic acid. And so that carbonic acid then actually reacts with calcium in order to form then and leach calcium from living things. And so that disrupts the exoskeleton of a lot of marine organisms. So we have lots of applications of acids and bases, but right now what we need to make sure that we are understanding basic chemistry, basic bonding, going back to our you must knows. Do you know the 3 subatomic particles? Do you know the 3 types of chemical bonds? Do you know the importance of hydrogen bonding and the properties of water? Do you know the unique properties of water and how they contribute to life on Earth? Can you interpret a pH scale? Do you know how changes in pH can alter biological systems, like ocean acidification? And then the importance of buffers in biological systems. So that's the one piece that we did not address, is what a buffer does. So a buffer is something that gets added to a solution that helps maintain pH. So it helps keep the pH constant. So we have buffers in our blood in order to help with that pH shift that might be happening. So that's what a buffer does. In AP chemistry, you will end up using lots of buffers and understand buffer ranges, but they help decrease any shift in pH so we can maintain a more constant pH. But a buffer itself is not involved in the chemical reaction that is occurring. So with that, that is my mini lecture and explanation on Chapter 2, Chemical Context of Life. And if you have any questions, pop into my office hours, and also I'll see you during class and I'll explain the exact same thing then. So with that, hopefully that helps you out, and I will see you guys soon. Bye.